Welcome to another episode of Wonders of Chemistry with Mickey G, and today we'll be looking at rates of chemical reactions. Now, one of the most important concepts when we deal with rates of chemical reactions is a theory called collision theory, which states that three factors must be met in order for a successful reaction to occur. Okay, number one. So reacting molecules need to collide with each other. Number two, they need to collide in the correct orientation. And number three, they need to collide with sufficient energy to break bonds. Now, there are a number of facilitating factors that help to achieve a successful chemical reaction, and these include, number one, the physical state of the reactants. So gases would react faster because they have an increase of surface area of contact with each other. Second would come liquids, and finally solids. And just to help consolidate this arrow is signifying an increase in reaction rate according to the state of the reactants. Number two, temperature. If we increase the temperature, the molecules move at a faster rate. And if they move at a faster rate, they're more likely to collide, and they're more likely to collide with sufficient energy to break bonds. So an increase in temperature increases the rate of a chemical reaction. Number three, the concentration of reactants. So if we increase the concentration of reactants, there's more reactants, which increases the probability that these reacting molecules will collide with each other. And if we increase the rate of collision, we increase the probability that some of these molecules will break bonds, which in turn will lead to a chemical reaction. Finally, add in a catalyst. So in order to explore how a catalyst increases the rate of a chemical reaction, let's quickly draw the energy profile curve for an exothermic reaction, including the position of the reactants and the products. Okay, so here's our graph. On the y-axis, we've got the enthalpy of reaction, which basically tells us how much heat or energy the reaction has. And the reactants are a higher energy state than the products. In order for this reaction to be activated, it needs to overcome this initial hump, which is termed the activation energy, which is the minimum energy required to break bonds between reacting molecules. The activation energy is not easily met in some chemical reactions. So for example, combusting magnesium in oxygen, we need to add an open flame to, say, a magnesium strip, and that gives the reaction the necessary kick to get over that hump. The larger the hump, the larger the activation energy. Now, a catalyst will find an alternative route that has a much lower activation energy. So when a catalyst is added to a chemical reaction such as this, the hump is not as big. So we end up with an activation energy that is significantly less than the previous one. So a catalyst reduces the activation energy, which in turn increases the probability that on collision, reactant molecules will have sufficient energy to meet the new required and lowered activation energy that's been provided by the catalyst.